Okay, well, thank you to the organizers for inviting me here. I've been many times to Bangalore, but never to the ICTS, and it's really a great pleasure. It's a fantastic institution that you've got going here. So I thought I would start with a picture, and if you gaze at this, for those who know, you'll see many people that you recognize, and three of us in this room were actually at this event. And so if you look carefully, you might be able to see those three people. But if you can't see them, let me introduce you to them. And there's something very interesting you're going to learn here. Okay, so the first one, this is me, if you look very carefully there. And next to me is a very small pink panther, if you look very carefully, okay? Let me show you Rama, who is here in the top left-hand corner, okay? And now let's look for a few more people. This is Phil Anderson, who actually still had his blonde hair at that time, okay? And just a few more people. This is Krishnamurthy, who still had his black hair at that time, okay? And this is Chandravarma, okay? And last but not least, and at this point I'll stop, this is Nick Reed, just there. Okay, so this is from a time about more than 40 years ago. And let's go to a more recent time, okay? And one of the things you notice here is that Rama is the one who hasn't really changed over 40 years. It's quite amazing. And he still retained his youthful appearance. This was taken in 2018. Be careful what you say. I think he's very youthful in his outlook. So anyway, I wanted to wish you happy birthday, Rama, though it's not your birthday yet, for the next birthday. And I really hope that you maintain your youthful appearance and your youthful attitude. So just to finish off, to connect up with this, I wanted to show you the only paper I have with Rama, although we've been friends and we've interacted over a long period, and I really appreciate what he did for me because he was kind of my surrogate advisor while I was at Princeton. He helped me to understand Phil Anderson, and he also suggested many wonderful papers that really helped me a great deal. And I kept looking at one of them that he'd written in Santa Barbara, the large N paper, and that was tremendously influential. So thank you very much. And this is the data that was fascinating to us. And here you see cerium copper-2, silicon-2, cerium palladium-3, and samarium hexaboride with their Hall constants. And we put together a model of skew scattering based on earlier work by Furt and Joule. And one of the things that came out of that model was a kind of nice fit to the product of the resistivity times the susceptibility, which really works for quite a few heavy electron systems at high temperatures until they become coherent. And so here you see along this line, the case that did not work, which is samarium hexaboride. And this downturn here is not only the result of the development of coherence, but the formation of topological surface states, something we could never have imagined 40 odd years ago. And so this is something that will come into today. These are the topological surface states on the 111 direction of samarium hexaboride. And this is a very new piece of data, which I'll tell you about in this talk. If I get to it. Okay, I blew 5 minutes. Yeah, okay, good. So, so this is work that I'll tell you about that I've done in collaboration with Vidya Madhavan, Anuya Aishwarya, Sekat Banerjee, and some Chinese collaborators, and Jean Mellet. And it's basically a new perspective on a curious property of samarium hexaboride. And my talk, if I get to all of it, I want to talk, first of all, about the challenges that face us at the current time, the challenges of materials that really are extreme deviants from our standard models. And these are the strange insulators, the strange metals, and the strange superconductors. And I really do think that they're a tremendous challenge to the next generation and the current generations of condensed matter physicists, and they require new approaches and new attitudes. And then I'll turn to talking about this particular challenge of samarium hexaboride and the new results that we have to present to you. Okay, so the standard model that have served us so very well begins with, of course, Drude model. Drude model was put forward by Drude before just a few years after the discovery of the electron. And no one knew about the existence of quantum mechanics, or barely, and they certainly didn't know about the existence of the Fermi surface. And yet, surprisingly, Drude's simple model survived the advent of the Fermi liquid and provides a beautiful description of many features of the electron gas, including the fact that the Hall constant is constant as a function of temperature. Of course, our entire world depends on the discovery of band theory and its implications, not only for our understanding in its broader form of the vacuum, but also our application of semiconductors to modern technology. And last but not least, BCS theory, this fantastic theory that describes the vast majority of superconductors, even the modern high-pressure hydrides, but it also involves certain features like the idea that magnetism is bad for superconductivity, and the notion that the only way we can get superconductivity is by pairing electrons. And so this is the standard model. And it's formed the foundation of solid-state physics for 70 years, and anyone who wants to study condensed matter physics has to be well versed in this, just in the same way that Pablo Picasso was a great draftsman. Okay, so let's now talk about the challenge that faces us today, and it's in part the transition between the extreme localization of electrons and the itineracy of electrons. And this is the Kometko-Smith version of the periodic table, organizing the D and F electrons in order of their degree of localization. So the 4Fs are most localized, the 5Ds are least localized. And as you go from left to right, you have increasing localization. And so the elements on the bottom left-hand side are all superconductors, all BCS superconductors, whereas the elements on the top right-hand side, with a few exceptions, are magnetic metals, particularly systems such as holmium, dysprosium, gadolinium, okay? And in between, you have this region where you're in transition. And it's this region of transition that is so interesting. In the modern context, we know how to make more localized and controlled localized systems with flat bands using Moiré systems. And what's rather dramatic is the fact that some of the things we've discovered in the bulk systems reappear in the Moiré systems. And so it's this dichotomy between the wave and the localized magnetic moment that is so fascinating to us. And it's this region in between where the strange materials appear, okay? And we wrote a little review on this subject a year ago. Okay, and so this linear resistivity of Lusco is a beautiful illustration of strange behavior, because it exhibits this linear behavior that punches right through the Joffrey-Regal limit and doesn't seem to notice it at all. And it's not unique to the cuprates. Here's a lovely recent illustration from Moiré tungsten diselenide. This is work by Kin-Fai Mak and collaborators and Xia. And here you see this beautiful linear resistivity, and a system has a very unusual Hall constant that is not temperature independent. In fact, it's so strongly temperature dependent that the way to describe it is in terms of the Hall angle, and the inverse Hall angle, or cotangent of the Hall angle, which describes omega c tau, is proportional to t squared. And this dichotomy between linear resistivity and t squared Hall angle is seen in many, many strange metals. And what goes next? Come on. Go. Okay. And so this is something very important, the fact that we crudely interpret this as a linear in T scattering rate, Planckian dissipation, but we have a T squared Hall angle or Hall scattering rate. And what is the origin of these two relaxation rates? Okay. Here's the system that I'll talk about today in more depth, samarium hexaboride. It has an emergent narrow gap of about 5 millivolts, and it shows exponentially activated resistivity, but this plateau here for years was something that couldn't be understood, and we now know it comes from surface states, which we interpret as topological surface states, but this hasn't allowed us to understand samarium hexaboride. There are still mysteries. In particular, there is the possibility that it exhibits quantum oscillations and has inside it some form of neutral Fermi surface. It also has for years exhibited this remarkable linear specific heat capacity, which is typically something of the order of 5 to 10 times that of metallic lanthanum hexaboride, which has exactly the same structure but no F electrons. And so how does the transition from a metal to an insulator give you a large linear specific heat and oscillations in the magnetization that are reminiscent of a Fermi surface? This is an open mystery, okay? And last but not least, this is a poster child for our emerging interest or re-emergence of interest in triplet superconductivity. This is uranium ditelluride. This is its phase diagram as a function of angle of magnetic field and strength of magnetic field. And what's remarkable is that not only this mere 2 Kelvin superconductor has already a very high upper critical field down here, but that in certain directions, that superconductivity can re-emerge and survive all the way up to 100 Tesla, even though it's a flyweight superconductor. This poses challenges that go beyond just triplet superconductivity, because such high magnetic fields go beyond the orbital limit for such a low TC superconductor. So these systems require theoretical descriptions beyond the standard model, and we don't know how far beyond the standard model, whether it's twinks to the things we know or whether it requires completely new approaches. For example, the surface states of samarium hexaboride required an entirely new perspective on insulating behavior, novel topology. We believe that the closeness to the critical point of magnetism is very important, but other ideas such as fractalization and possibly new forms of order parameter may play a role in these systems. And in some ways, that's an opening statement to what I'm now going to talk about in the context of samarium hexaboride. Okay, so let's swivel now to samarium hexaboride. I've got 20 minutes left. That's wonderful, just enough time. So samarium hexaboride, let me tell you about it. This is the data that I showed before. This is the resistivity with its exponential enhancement here. This is the log of the resistivity, and here it's plotted versus 10 to the 3 over T. So as you go down in temperature, it forms this plateau here. And for years, people tried to understand why it was that they had impurity bands, even though they'd worked so hard to make the sample very, very pure. And then it became clear that actually this is a surface conductivity. And in fact, around the same time, the whole idea of topological insulators came along, and we were able to take these ideas and propose that samarium hexaboride might in fact be a topological insulator. And in fact, the physics of why it should be so is very, very straightforward. This is a system with very flat F bands and a D band which comes down at the X points like a sword of Damocles. And when this crosses through, you have 3 crossings, 3 band inversions, then force you to form surface states at on the surface, because D bands are even parity and F bands are odd parity. Okay. And so this is interesting, however, because this system is an emergent semiconductor. It's the local moments or the valence fluctuations that enable you to form the narrowband semiconductor. And to some extent, you can think of it like a Kondo lattice. And so the Kondo lattice involves the fractalization of spins into heavy electrons. And so this is topology meeting spin fractalization. And so it makes you wonder, well, could there be new forms of spin fractalization? And are there new mysteries to discover? So these are the surface states of samarium hexaboride. On the 100 state surface, you actually see 3 Fermi surfaces. On the 111 surface, you actually see this hexagonal arrangement of Fermi surfaces. And these are completely consistent with the vanilla picture of a topological insulator with this structure. And yet this system still has surprises. And what I want to focus on today is an aspect of the topology that hasn't really been explored very much, particularly in the context of strongly interacting topological insulators. And so one of the important points here is that the transition between a conventional insulator, Ci, and a topological insulator can be thought of in the particle physics language as a Dirac system in which the mass changes sign. And so this was understood years ago by the particle physicists. They understood that when the mass inverts, you get domain walls, and those domain walls contain gapless excitations. This is the idea of Jacqueff and Rebbe, and we can extend it to understand topological insulators. We can really think of a topological insulator as an insulator in which band inversion inverts the mass of a Dirac equation, and you therefore get surface states which are domain walls in which the mass changes sign. Okay. So this is a domain wall, and that enables us furthermore to understand the emergent physics of the surfaces. Okay, but in fact, there's a deeper physics to this topological quantum critical point. At that particular point, the Dirac equation starts to dominate the physics, and there are certain features of the Dirac equation which become very important at that point. And one of the things that in condensed matter physics we never thought would be important is the word anomaly. Anomaly refers to a symmetry of the system which is not consistent with the regularization of the quantum field theory. Whether you put that system on a lattice or you do a particular cutoff scheme, that particular nominal symmetry is broken. And that happens in the Dirac equation. That anomaly is known as the axial anomaly. It's because there is, in some sense, the number of particles that are rotating right-handedly and left-handedly would normally be conserved, but it's not. And one important piece of physics that comes out of that is that it is this topological behavior. So one of the things you can do is that you can actually bypass a topological quantum critical point by giving the mass in the Dirac equation a phase. More precisely, this is, you have to include a rotation in this axial direction. And when you do that, you can continuously go from a conventional insulator to a topological insulator. And this is presumably what's happening at the surface of a topological insulator. So this is the kind of rotation that occurs inside the Dirac equation. And thanks to the work of the pioneers of this field, we know how to integrate out, to follow the effect of this rotation here. And it turns out that this rotation has a non-trivial effect on the measure of the path integral. And what that does is it kind of winds up the electromagnetic field and introduces this additional axionic coupling between the electric field and the magnetic field. It is actually true that if you do the path integral with this I theta here, then what you get out is this term plus this axial coupling. That's an identity from particle physics. And so it turns out that since this is topological in nature and that lattice systems inherit the topology of the topological quantum critical point, that we expect that topological insulators contain this additional coupling, even samarium hexaboride. Now, it turns out that if theta is equal to pi or minus pi, this becomes invisible. It only becomes visible if at the surface of the system, at the domain wall, theta changes continuously. And you may notice a similarity with the physics of Bose-Einstein condensation and superfluids. Bose-Einstein condensation is predicted as a property of non-interacting bosons, but superfluidity requires an interaction. And that's because the phase requires a rigidity, a stiffness to get superfluidity. In a similar way, in order for a non-interacting topological insulator to acquire a rigid axionic effect, the phase here has to become rigid. And that rigidity means that at the surface of the system, you have to have broken time reversal symmetry. And when you have that broken time reversal symmetry, you develop this coupling between E and B. What that means is that when you differentiate this action with respect to the magnetic field, you get a magnetization, and that magnetization is proportional to E. This is the property of an axionic insulator, and it's long been assumed that this requires an insulating surface state. And what I'm here to tell you about is that we have data that shows that you don't require an insulating surface state. You can have an axionic insulator which has conducting surface states, and this is very important for the physics of samarium hexaboride. So let me show you the data, okay? But the message behind this is that if you could have this theta becoming continuous between the inside and the outside, you'd have a broken symmetry on the surface of your system. You'd have a phase transition on the surface, which would manifest itself that below that phase transition temperature, an electric field would produce a magnetization. Okay. Let's now go to the physics of samarium hexaboride. This is a discovery that was made by the Madhavan group at University of Illinois, Urbana-Champaign. They took nanowires made of samarium hexaboride, here they are, and they used them, and they discovered that the surface states of these systems could be used to actually do tunneling experiments. And so they tried it out, and they took it across the surface of various antiferromagnets, and to their amazement, they discovered that these nanowires could actually see magnetic moments. They could see localized magnetic moments. They could see the staggered magnetic structure of this particular system, iron tellurium. Okay, so let me show you what that really means in practice. So this is the dI by dV showing the tunneling into this system. It shows various features that we expect for a condo insulator. There's a kind of gap. It's not a perfect gap. And you see asymmetries in this structure, which are thought to have an origin in various Fano resonances in the tunneling. So if you take chromium and you take it across the surface of iron tellurium, you see a spin contrast. If you lock it in a fixed current and you slide it across, you see that its height rasters up and down periodically with the spins of the underlying lattice. And that's because when the spin is aligned with the spin in the chromium, the tunneling occurs more readily. Okay? If the spin is oppositely aligned, you have to bring the tip closer to the surface in order to have the same current. And so the feedback mechanisms in the STM automatically adjust, and they produce this alternating pattern. And what is known for chromium is that if you reverse the voltage and take it backwards, it just follows exactly the same path. Okay, so same current, equal opposite voltages, you get the same result. When you do this for samarium hexaboride, it shows again this same spin contrast. So you take it across and you run it across the surface, and lo and behold, it produces an up-down behavior. But if you then reverse the voltage, something remarkable happens. It reverses its behavior. And so the spin contrast changes sign with the applied voltage. Okay. And when this was first seen, the Urbana-Champaign physicists interpreted it in terms of planar tunneling. And the planar tunneling, they argued that because the spin is momentum locked to the momentum, that when you reverse the momentum, you reverse the spin. And that's what you're seeing here. Opposite voltage leads to opposite current, which means opposite spin polarization. Okay. Yes. Yes. Chromium is spin polarized. Yeah, absolutely. Yes. Yes. Okay. Right. Yeah, it's an antiferromagnet. Yeah. Samarium hexaboride, even if you think it's spin polarized, you have to understand why it reverses the voltage, right? And so the interpretation given by the Urbana-Champaign group was that this was not spin polarization. It was the polarization of a spin current, okay, that was changing as a result of voltage inversion. But the problem with this interpretation is it relied on the notion of planar tunneling. It relied on the notion of momentum being conserved in the tunneling process. And yet the data showed atomic resolution, showing that actually you're tunneling through a penultimate atom on the tip of the nanowire, okay? And if you've got atomic resolution, there is no momentum involved at all that's conserved. It's a sum over all momentum. And when you try to investigate that in detail, The simple Bardeen tunneling formula cannot explain this phenomenon. So we got very interested in trying to understand the physics. And Jean Millet said, well, could it be axionic physics, which we didn't even know about? And I was extremely dubious about it, but I'll show you the argument that changed my mind. Okay. So this is the experimental fact. And let me show you a bit more detail. One of the things you can do in this is with the chromium tip is you can compare two Fourier transforms of the tunneling, and one of them is the tellurium atom, and the other is the iron atom. And so by comparing the two, you can actually look at you can contrast the strength of the spin sensitivity, the spin contrast, with the plain electronic featureless physics of the tellurium. But if you do this for samarium, you see the two peaks again, but the contrast of the samarium is voltage reversible. And in this particular picture, it's actually opposite to the tellurium. Okay, so what does this mean? Okay. And so the first thing you need to do is you need to say that, well, this really does mean there is a spin polarization on the samarium tips. Okay. To get an estimate of that polarization, you need to compare the strengths of these features in the chromium and the samarium scans. And you can do that by comparing the relative ratios of the antiferromagnetic to the tellurium peak, and then taking that ratio between the two, and all things being good, this gives you a rough estimate of the ratio of the moments. And so the samarium moment seems to be about 0.1 of the chromium moment, which gives us something of the order of 0.1 or 0.4 magnetons, okay? But what's weird about this magnetization is it reverses with the voltage. So let's now look at what that means. Moreover, this spin contrast physics developed somewhere around 10 Kelvin. And a big deal was not really made in the paper that observed this, but this has the elements of a phase transition. Namely, below 10 Kelvin, the spin contrast turns on. Above 10 Kelvin, it switches off. Unfortunately, they didn't do any hysteresis measurements in the original round of experiments, and the key experimentalists moved to Cambridge, Massachusetts, and we're still waiting for those measurements still to be done, the hysteresis experiments. In the meantime, we can look at whether this might actually be axionic. And so if you have an axionic system, the coefficient between E and the magnetization is fundamental, and just determined by the sign of this theta here, okay? And so we can make an estimate of how big that would be. And of course, in the case of samarium hexaboride, since you've got strong spin-orbit coupling, you cannot separate orbital magnetization from spin magnetization. The two are really one and the same. And so if we look at this, we can actually write the orbital magnetization or the spin magnetization of samarium in this simple form. This is the ratio of the size of the unit cell to the Bohr radius cubed. And this is the ratio of the tunneling field, V, the voltage divided by the distance, to the tunneling field inside a hydrogen atom, okay, which is this huge 10 to the 12 volts per meter. And when I started thinking about this, I thought all is lost. This is going to come out to be 10 to the minus 9 Bohr magtons. But when you sit down and work this out, you've forgotten about something about the fields in an STM tunneling tip, which is, although you have millivolt voltages, the gap between the tip and the substrate is something like 40 picometers. It's this incredibly tiny scale. And so the ratio of the two doesn't give you quite the field inside a hydrogen atom. It's within a factor of 1,000, okay? 10 to the 9 volts per meter. And so when you take into account the unit cell size of samarium hexaboride, you actually get in your back of the envelope estimate for 40 millivolts about 0.1 Bohr magton. So it's in the it's in the right ballpark, okay? Does it make sense? Can we make this consistent with the fact we've got simple Bardenian tunneling here? So that's what we went and did. We said, look, okay, let's look at this data more carefully, and let's use the Bardeen tunneling formula. If we Fourier transform the Bardeen tunneling formula with respect to position on the surface, we can produce this term here. And we know that the Fourier transform of of the spectral function on the substrate is the magnetic part of the Green's function. And so putting that into this expression here, I think something's been cut off my equation. I'm missing. Oh, that's right. So this is the magnetic part of the tunneling in the tip. Okay, and unlike a conventional system, if this is axionic, then this tunneling component depends not only on the frequency, but also on the applied field being picked up by the tip. If there is an axionic behavior, then as I turn on that field, this thing will acquire a term proportional to a Pauli matrix. It'll acquire a magnetization. And so what we then did was to make a very simple model and pull it out of the data. And in that model, we assumed that this magnetization was proportional to the voltage. And we could fit the data very nicely with this fit, and out came this spectral function, which is really rather curious. This is actually m time, which is v times x, showing the fact that the magnetization reverses with voltage, and curiously has this node at some point here. This is because the spin contrast shifts by half a wavelength when you go above a certain voltage experimentally. We don't yet have a microscopic model for this. Okay. Yes.
Just to understand, so the picture is that the E field from the STM tip is reducing
yes.
surface, and then it's just this chromium story.
Yeah. So then it becomes like chromium, and the only real difference is that the magnetization on the tip reverses with the E field. Okay. What's really neat is it's not really a nonlinearity. It's literally that the magnetization is proportional to the field that penetrates the tip. So it's actually linear, which means the Green's function, the magnetic part of the density of states in the tip, will be proportional to the electric field. And so you've got this, the nonlinearity comes in because when you do STM, you're picking up the part of the Green's function, the density of states, at an energy equal to E times V. But now, in addition, you've got an electric field coming from the voltage that polarizes the tip. So you have to pull those things out. What you really need is a whole bunch of an extra large set of data at different tip heights with different electric fields to really pull it all out. And we don't have that data yet. That's really waiting. So, but in the meantime, we do believe there's enough evidence to show that the surface of samarium hexaboroid is axionic. Okay. And this raises all sorts of questions, one of which is, what is the nature of the broken symmetry, the time reversal breaking symmetry at the surface? And we can rule out simple magnetism, simple ferro or antiferromagnetism, because a finite offset M0 doesn't fit the data. So it's more likely exactly what Wilczek imagined. It's a complex mass, which in the context of heavy fermions, mass becomes the hybridization. So it's probably a part of the hybridization that breaks time reversal symmetry. And this can come about very naturally on the surface of samarium hexaboroid, because on the surface, the D states and the F states can hybridize at the same samarium site due to the loss of inversion symmetry. And this introduces another Kondo channel, which then we believe, although we haven't checked yet, picks up this anomalous phase factor with the hybridization in the bulk. That's what we think is going on here, but it's a developing story. Okay, so that's the end of my story. These are my conclusions, and thank you for listening. Planckian dissipation, yes.
Planckian dissipation, how the Planckian physics come at this scale?
Okay, first of all, the Planckian dissipation wasn't relevant to samarium hexaboroid. It was a comment on the strange metals. Okay, okay. And so what is your question?
There's a Planck scale.
Yes.
It's a very small scale, 10 to the
Well,
power
okay, so
-30
this is the danger of words. This is a wonderful word that was coined by the late Jan Zahnen, who was fascinated by the connection of black holes to condensed matter physics. And the term has stuck. It's nothing to do with physics at the Planck scale. It's more due to the fact that the only constant that comes in is Planck's constant. Okay.
Okay, sir. Yeah, I ask one more question.
Sure.
In the one slides you introduce the concept of the axionic physics.
Yes.
So that it is so fast, I'm not able to understand.
Well, join the club. It's something that I'm desperately trying to understand. Okay. For me, I have a very simplistic understanding. Okay. And the simplistic understanding is that there is an emergent term in the free energy which goes like E dot B. Okay. If you want a little bit more about this,
Any reference? Any reference?
there are lots of references, but they're spread around is the problem, and it takes a while to get into them. But fundamentally, there is actually a path integral. There's a path integral in relative physics quantum mechanics that can be done exactly. And basically, when you introduce, let me just, when you change the phase of the fields, okay, nominally, if you assume that the Jacobian of the path integral doesn't change, you acquire the law of conservation of axial current. But when you take into account the Jacobian of the path integral, it turns out, which is the part that determines, which is the change in the measure of the fields due to doing this small rotation, it turns out that that additional term remarkably develops this E dot B term. In condensed matter physics, it's like a Berry phase. It's closely analogous to the Berry phases that come up in various topological field theories. And so it turns out that this term really ought to be there for every single topological insulator in the world, excepting that this theta field probably has no rigidity at the surface of the system. So it's a product of particle physics. That's the best I can do. Thank you.
Yeah,
sure.
so just to make sure I understand the proposal, to say there's a complex hybridization or in the Dirac equations, the complex mass, but I guess what you're envisaging is that it's a doped version with a complex mass. Is that right?
No,
The
okay,
chemical
so you're asking why the gapless surface states, I think, is what you're coming at. Is that what I'm understanding?
Yeah, so where is the chemical potential in this?
The beautiful thing is that we understand the surface states of samarium hexaboride have great big Fermi surfaces. You saw them in those pictures. And that's because in some sense, the Dirac cone has been dunked into the Fermi sea, okay? In reality, it hasn't been dunked. It means it's come back above it. You just can't see it in the ARPAs anymore. It's above the Fermi energy. It always has to be there in a topological insulator, that Fermi surface. So that when you break time reversal symmetry, you open up that crossing point, but it doesn't gap out the surface states. And so if that's what you mean by doping, we envisage that there are gapless states on the surface which aren't affected by the broken time reversal symmetry. And hence it remains metallic, even though it's also axionic. Of course, because it's metallic, that means that electric fields can't penetrate indefinitely inside the system, but the screening is very weak. And so it gets in far enough to create the magnetization. That's our picture.
But wouldn't this show up in, say, polar Kerr rotation or things like that?
Should do, hasn't ever been done.
Okay.
Yeah. Right. Yeah.
Yes.
Yes.
So you showed that the magnetization was responding to an electric field.
Yes.
And that's how it was switching.
Yes.
And I was wondering if there was data also as a function of magnetic field.
No.
Modeling data.
And the important thing is that the magnetic field you can create is terrestrial, whereas the electric field you can create is astronomical because of the nature of the STM experiment. So if you put 1 Tesla into that, the amount of electric polarization you get out is absolutely tiny, and also would be very difficult to see because the surfaces are conducting. So you couldn't actually pick them up.
Right.
Yeah.
Okay.
Yeah.
Thanks.
I have a question. Is this picture a generic picture or is it very specific to samarium hexaboride?
So
in particular, does boron have any role? Because you talked about the FD hybridization, but boron P, I guess, will also have some role.
Yeah, as far as I understand, the band structure of samarium hexaboride and also of lanthanum hexaboride are very simple. In fact, samarium hexaboride is basically the lanthanum D bands plus the samarium F bands. There's nothing else there. So it's a very, very simple Fermi surface structure. And so the boron, fortunately for me, but unhappily for you, the boron doesn't play a major role, and I can just think about the problem as effective hopping between F and D states on the samarium atoms and not worry about the other things, I think. Yes, yeah.
But it's then
Well, the generic part comes in that this axionic coupling should be there for all topological insulators, excepting, this is just pure speculation, the stiffness of the theta field is probably dependent on the system. But it might be that you go back, and if you get them adjusted to exactly the right point where they really are insulating in the bulk, that you can see this transition in other systems. Yeah. Yeah.
So we thought a lot about these kinds of things in the context of the work we did on normal bismuth selenide, let's say.
Yeah.
And so there, to see axion electrodynamics, we did terahertz polarization experiments. And it's very essential to do it at reasonably high frequencies, because otherwise you get shorted out by there's always a little conduction, bulk conduction. Surface conduction, if it's a pure surface Hall effect, that doesn't matter. And in fact, that's the effect itself.
Right.
So if you have anything else that conducts, you basically won't see the axion effect because you can't develop polarizations, surface currents end up dissipating. So in order to see it, you have to be at a finite frequency. Otherwise, it's like a capacitor, which is like a leaky capacitor if you're developing polarizations and these kinds of things. So then I'm struck by the STM experiment. I actually don't know how it's done, but is it done at finite frequency?
No, it's DC.
But is it truly strictly DC, or that's just the way
Wow.
Okay, I'm not sure about that, but I think it has to be.
It's DC. It's
Yeah.
definitely DC.
Just-
Yes,
yeah.
definitely DC.
So then
It's
then I
just
don't
good old-fashioned STM.
Yeah.
Now,
So
what's new, the new feature about this is that in the past, the theoretical picture of the axion has purely emphasized the orbital part of the magnetization, not the spin part. And the orbital part can't be really picked up in an STM experiment, but the spin part can, okay, in the very same way that chromium picks up the magnetization. So if there's a spin component to the M in the axionic system, you can pick it up with tunneling.
Yeah, so I'm confused. I think the dissipation is important. You can't see it without it. We looked, by the way, at SMB6 for these rotations, and we saw.
Yeah.
Okay.
Hello. Yeah, Piers.
Okay.
Yeah. So.
Yeah.
So no, my question is regarding this two relaxation time scenario. So Anderson argued that there are two relaxation times, but there is a parallel argument by Gorkov and Teitelbaum. So they argued that there is one relaxation time only that goes as T square. So for example, the conductivity in the 2D model goes as NE square tau divided by M. So they argued that the tau has 1 by T square, but the N, the number density, is actually proportional to T. Because they say that this is the excitation gap to the charge carriers.
Yes.
So then what happens that the conductivity goes as 1 by T, the resistivity proportional to temperature.
Yeah.
So they sort of try to argue that one can rationalize this two relaxation scenario just using that one relaxation scenario plus the gap to the charge excitations, and then they connect with the temperature dependence of the Hall coefficient. The Hall coefficient is also 1 by T, roughly goes as 1 by T. And then because the Hall coefficient is 1 upon NEC, N is the number density. So N is proportional to temperature. So they very nicely sort of try to rationalize that. And recently we did some work. We saw that where there is a magnetic transition, the system near a magnetic instability, that kind of gap to the excitation exists, then one can understand this two relaxation scenario in terms of just one relaxation scenario. So I would like to know your comment. What are your comments on this? So should one stick to Anderson's idea of two relaxation times, or one can have this Gorkov-Teitelbaum thing? How do we rationalize this?
I think that's a very interesting scenario, but then the focus would then be understanding why the density of carriers coming in would be proportional to the temperature. There's no pseudo gap in these systems. This is in the overdoped regime. That's the problem. But anyway, I don't want to diss it. I think the great thing about science is that you can have different theories. The most important thing, though, about your theory is that it can be disproved. So you need to ask the question, what would disprove my theory and then have someone do the experiment. But if you can't answer the question, what would disprove my theory, then you probably don't have a theory.
Hey, Piers, very quick question. When people first got very excited about this chiral anomaly in these topological systems, they were using this idea that the E dot B term generated a negative magnetoresistance, a longitudinal negative magnetoresistance. That was, I think, that's somewhat controversial, and it was certainly an indirect evidence. But so I'm just curious whether in samarium hexaboride they see this negative longitudinal magnetoresistance at all.
Yeah.
Only in the Dirac series?
Oh, they've let me off the hook.
Okay.
I was going to say I don't know, but I would defer to other expert opinion on that. Okay. Yeah. Okay. Thank you, guys. Oh.
Yeah. How would your formalism sort of result if you have a massless Dirac equation and try to recover, say, the electronic properties of graphene? Would that be feasible?
Okay, so the question is, what would happen if you did this, use the phenomenology of relativity for graphene, which is basically massless? And the answer to that is that graphene is only a 2-component Dirac fermion, not a 4-component Dirac fermion. So this formalism doesn't work in that context, I think, is my answer, but I'm not quite sure.
Thank you.
Right.
Very interesting.
I think we have to call it a day for this talk, and we can continue discussions during lunch. So I'll call the next speaker.
Thank you.
It's time to see Coleman.
Thank you, Arthur.
As usual.